Implicit differentiation, I'm not going to say too much and go in too deeply into this, but this is something for the most part, and I see it all the time. You guys do a really good job. Most high school teachers really emphasize implicit differentiation. So, of course, the idea here is that we have an implicit function such as x squared plus y squared equals 100. We know that this is an equation of a circle with radius of 10. And the reason why it's an implicit function is because we do not have one variable explicitly in terms of the other variable. Now, some implicit functions can be rewritten explicitly, okay? This is not one of them. It'll have a plus and minus. It could be explicitly written as two functions, but not necessarily being solved. So there are stuff like if it was x plus y squared, right, equals 100, and you could solve for x, and that turns it into an explicit function of x in terms of y. But we don't want to do that extra step. How do we work with just what we have right here? Well, we could do implicit differentiation. And in this problem, the question is, what is dy dx? That's what I'm trying to figure out. I could ask you, what is dx dy? How much is y changing when x changes by 1 unit? So if I increase x by 1, how much is y changing at that instant in that rate? Okay. Basically, it means that this is giving us our vertical change, right? So if x is increasing by 1 unit, how much is y going to change? So if we have dy dx equals 0, that means x has moved. We have increased the x by 1 unit from point to point, but then the y hasn't gone up. And if dx dy equals 0, that means y has gone up and there's no movement in the x direction. And the implicit differentiation portion is actually the first piece. And what it says is we're going to take the derivative with respect to x, in this case, because I want to find dy dx, of x squared plus y squared. And I'm going to set this equal, whatever I do to one side, I do to the other. So this is going to equal the derivative with respect to x of 100. Just to be consistent. And that gives me 2x plus 2y times, now technically what's happening here is it's all chain rule. So it's 2x times the derivative of x with respect to x, dx, right, which is just 1. So since I'm taking the derivative with respect to x, the derivative of x squared is just 2x. 2x times 1, if you want to get a little bit more technical. So the derivative of y squared would be 2y times dy dx. If you feel comfortable using the notation y prime, feel free to do that on your P sets. I'm a personal fan when I do these problems of doing dy dx, just because when we start doing different variables and we have x and t's and we start doing parametrics, it can mean a little bit more to you when you keep that notation there. Is equal to 0. This gives us 2y dy. Now that is the implicit differentiation, but now we want to solve. So the next part is just algebra. Equals negative 2x. So dy dx is equal to negative x over y. And so the main thing that I want to show you here, and again, this is not something I'm going to spend a lot of time going over. I'll kind of leave it here because your expertise has already shown me that I don't need to go too deeply in terms of some different examples. We have some problems in workshop. You have a problem in your P-set. I could ask you tangent line questions regards to this, but we have these problems. What I really wanted to at least spend a little bit more time on and going through an example is a second derivative. And basically that means we're finding the derivative with respect to x of the derivative of y with respect to x. And technically it's like that. So if I was writing this a little bit in a better notation, d dx of y, this is what we are doing right here. d dx of of y, the function being that y. And that's why when you see it, this is oftentimes why we use the notation d squared over dx squared, because it's d, that's the d squared, dx, that's the dx squared. And actually, I could even go a little step further, of y, which is d squared y over dx squared. So that's why that notation is there written that way. Okay, I always see that it's like, oh, why is this squared and it's not d dx? You're taking the derivative with respect to x. And so in our example, we want to find a derivative. We want to find the derivative with respect to x of dy dx, which is the derivative with respect to x of negative x over y. Okay, that's what we're doing. This notation should also help us later on when we get to parametrics again and we find the second derivative there. That's why I have tried to do a lot of setup. So d squared y over dx squared, the second derivative, using quotient rule gives us negative 1 y minus dy dx times negative x. I like to just keep the negative on top as part of the negative rather than doing it all factor out the negative. It's my preference. Over y squared. Negative y plus negative x over y times x. And the idea here is that I want to find the derivative just if I know what dy dx is. Because remember, dy dx was negative x over y. All over y squared, which is equal to negative y minus x squared over y all over y squared, which cleans down to negative y squared minus x squared over y cubed, right? Multiplied by y over y. Now that's nice and pretty, but we can also clean it up even more because, and this is just ideas, we know this is the same thing as negative y squared quantity x squared over y cubed. And what does x squared plus y squared equal? Going back to our original 100. And we get negative 100 over y cubed. So we were able to find out that the second derivative, actually the x variable doesn't even matter. It doesn't even matter what the value of x is. It only matters what the y value will be on that coordinate, negative 100 over y cubed. So I might request for you to find the derivative or the second derivative only in terms of x and y, which means usually you're just plugging in that dy dx. And I might ask you to only find it in terms of one variable. This can help simplify a lot of different problems. Remember, you know prior relationships. So I gave you a relationship, x squared plus y squared equals 100. So throughout that problem, if you see an x squared plus y squared, you can change it to that value 100. We're here to 55, right? Derivatives of inverse functions. So I'm going to use this idea of what we just learned as well. There's a couple of ways of going about doing what we're about to do, and this is going to help us do a couple of proofs along the way. So an inverse function is defined such that f of the inverse function of x is equal to x. It undoes the operation. So if I plug in x, I get some value, and I plug that value back into the inverse, it should spit me back out the original value that I started with. Oftentimes we defined, we have the inverse function. We'll just call it g of x so that there's less things. So f of g of x is equal to x, given that x is an inverse function. And now we can apply that implicit differentiation idea. We can take the derivative with respect to x on both sides. This gives me chain rule f prime of g of x times g prime of x, which again is the inverse function, is equal to 1. So g prime of x is equal to 1 over f prime of g of x, which proves to us that the inverse function of x derivative is equal to 1 over f prime of the inverse function of x. This is a nice, straightforward formula that we can utilize. Of course, if you had the problems and you're trying to find a derivative, you can utilize that implicit differentiation. I'm going to show you that a little bit later on in a future lecture when we're doing like arctangent and arcsines. But this one is very helpful for us. And then, of course, you're going, so why, where am I going to use that? Well, I could ask you for just any type of explicit function that's our like tabular problem. I know that was always heavily on the AP exam. But I like this problem because if we know from our algebra, if f of x is equal to e to the x, then the inverse function of x is natural log of x. Yes. I hate when people say pet peeve. At least it didn't say in. I have students that say in, and it's like, we're in, February, and they're still saying in. It's like, natural log of x. So we know that this is true because e to the natural log of x is is just simply x. They can't, they cancel each other out. We also know that the natural log of e to the x is just simply equal to x. They cancel each other out. So we have a new proof, something new to show. What is the derivative of the natural log of x? Well, don't worry, no definition of the derivative here. We can use what we just learned. This is the same thing as the derivative of the inverse function of x, which is ln, right? Which is equal to 1 over f prime of the inverse function of x. It should also be known that f prime of x is simply e to the x. We've already shown that earlier. And therefore, we get that this is equal to 1 over e to the natural log of x, which is 1 over x. So the derivative, so there's our proof. So the derivative of the natural log of x is equal to 1 over x for x greater than 0. It's important to note that as well because natural log of x is only defined for values of x greater than 0, so therefore its derivative is only defined for x greater than 0. Don't worry, I'm going to get to what you're thinking about very shortly. If you had wanted to as well, another way you can prove this derivative using just, if you wanted to do an implicit proof, is that if y is equal to if y is equal to the natural log of x, then x is equal to e to the y, and then you can go from that direction right there. So that's how you would do it. You would take the derivative using that implicit function, and you can also prove that the derivative of natural log of x is 1 over x that way as well. Not going to do both, though. I'm just going to give the one. I wanted to throw in the chain rule version. And that just says that the derivative of the natural log of u, where u is a function of x, is 1 over u times du dx. Most of you might just remind it as u prime over u, however you want to do that one. Derivatives of absolute value functions. I know most of you are kind of like, well, wait, what about the natural log of absolute value of x? Well, we don't know how to get to there unless we know what the derivative of the absolute value function is. So let's bridge that gap. We define y as the absolute value of x. And how do we write the absolute value of x as a function, not piecewise? What is another way of rewriting the absolute value function? Yeah.
X squared to the square root of the square root.
There, you said it backwards, yes. So the square root of x squared. Right? Think about it, right? If you take a value, square it, you're going to get a positive, and then you take the square root of it, and the square root of anything, of a number, of value is positive. Remember, a lot of students are like, well, wait a minute, doesn't square root give you plus or minus? No. Solving an equation of x squared equals and taking the square root to solve an x gives you pluses or minuses, a plus or positive solution. When you're evaluating a square root, you still get one positive answer, which is the same thing as x squared to the 1/2, which I think was the way you were trying to say it. So if I want to take the derivative of the absolute value of x, it's the same thing as taking the derivative of x squared to the 1/2, which using chain rule gives me 1/2 x squared to the negative 1/2 times 2x. Okay, well, the 2's cancel each other out. So I get x over x squared to the 1/2, which is x over absolute value of x. So the derivative of the absolute value of x is x over the absolute value of x. Now that leads us to what we really wanted to know. What is the derivative of the natural log absolute value of x? Well, it's a chain rule problem. This is going to give me 1 over the absolute value of x times the derivative of the absolute value of x, which is 1 over the absolute value of x times x over the absolute value of x, which is going to give me x over, what is it? Actually, it doesn't really matter. The absolute value doesn't even matter anymore. Because what's the absolute value of x squared? It's just x squared, right? Because x squared is always a positive. So yes, it's absolute value of x squared, which is just x squared. The absolute value no longer matters, which is just going to give me 1 over x. So the derivative of the natural log of the absolute value of x is 1 over x. The absolute value doesn't play a part in the answer of that. And for those of you that are always like, oh, what happened to that one? Also, just in terms of the chain rule, the derivative of the natural log absolute value of u just becomes 1 over u times du dx. So we have about 12 minutes. Yeah, it looks like I probably won't get to the L'Hôpital piece at all today. So Gwen, so you could probably update that for workshop. Okay? No, but it will be in future ones, our problems. We'll see what we have. All right. Logarithmic differentiation. Ugh. Some of you will mix this up with L'Hopital type problems, level 3 type L'Hopitals. They are different, so please do make sure you do note. And those, given some individuals who took the KBA last night, I gave an example of that problem. And a lot of people were trying to do logarithmic differentiation, or they were trying to do L'Hopital. It was like a complete mix-up, and that was one of the. It's always one of the interesting things to see in terms of it. First off, from pre-calc knowledge, we know that the natural log of a to the b is equal to b times the natural log of a, the power rule of logs. And we also know that so we know that's true. We also know that the natural log of a plus the natural log of b is equal to the natural log of a over b, and go both ways. The a times b, the natural log of a minus the natural log of b is the natural log of a over b. So these are just some rules that you should remember. They will help you in later problems when we are doing some, especially when L'Hopital, when we're going to try to do some differentiations and we have to prove that we had 0 over 0, and you're like, but I don't want to take the derivative that way. Well, if I split it up, I'm good again. Okay, so moving back and forth can make a lot of problems very easy for you to practice, go through. So in these problems, we want to find the derivative of a function of x to a function of x. So g to the x raised to h of x. Okay? And I like to think of these problems as multiple steps. Okay, so I'm gonna do on two sides. On the left-hand side, I'm gonna treat this as a function of x. So g of x, f of x is g to the x to the h of x. In this case, f of x is g of x to the h of x. Okay. My first step is to take the log of both sides. Right. Well, my step 2 are the first thing I'm doing. So I get the natural log of y equals the natural log of f of x, the function that I want to take the derivative with. While doing so, I get the natural log of f of x would be the natural log of g of x raised to the h of x, which gives me the natural log, or which gives me h of x times the natural log of g of x. The next step I'm going to do is I'm going to differentiate both sides. So I'm going to take the derivative of the natural log of y equal to the derivative of the natural log of f of x, which is going to give me 1 over y times dy dx, chain rule, which is going to give me the derivative of h of x times the natural log of g of x. What am I going to do on that right-hand side? What am I going to do here?
Bring h of x up top.
No, don't need to do that. How am I going to do this? Typically.
Product rule.
There we go, product rule. Overthink it sometimes. We overthink the word sometimes. It's most likely to be a product rule that we're going to have to do it. So we're going to actually take the derivative. It's going to be usually a function and a natural log of a function in terms of your product. Okay? Has there always been construction? Was it yesterday, last time too? Okay. Step 4. Which is basically the last step, that dy dx would therefore equal to y, because I'm going to multiply by y on both sides, times the derivative of the natural log of f of x. I know that kind of looks weird, but I mean, because there's so many different things going on here. So dy dx equals g of x raised to the h of x times the quantity of whatever the derivative of h of x times the natural log of g of x is. So you're going to have some type of product rule inside here. So we have the original function. Don't forget to rewrite the original function back. Don't leave it in terms of just y times. And then the actual derivative. I have a little bit of time. Ooh. I'm going to do this. I'm going to do one quick example so that you can do the other one in workshop. The derivative of x to the x, a very common, straightforward problem, just because a lot of people don't cover logarithmic differentiation in high school. So in this problem, I'm going to define y as x to the x, okay? So therefore, I'm going to get the natural log of y is equal to the natural log of x to the x. So the natural log of y is equal to x times the natural log of x. I differentiate both sides. That gives me 1 over y times dy dx equals product rule, 1 times natural log of x plus 1 over x times x, which finally gives me dy dx equals my original function, x to the x, which is just the y, times natural log of x plus 1. You can also use logarithm, and it's kind of confusing because logarithmic differentiation can be thought of two different ways. This method right here, and also what really logarithmic differentiation means is that we're utilizing the properties of logs to turn something that can be very complicated in differentiating into something that's much more manageable, okay? I'm not going to do the following problem. I'm going to leave it to you. You have or at least an example in your workshop tomorrow. So for example, we can do really complicated problems, and either this problem or something different is we want to find dy dx for something like y equals the square root of x squared plus 1 quantity cubed all over the cubed root of x cubed plus 1 to the 4th. Something that looks, if you just try to use quotient rule and you just try to be a hammer and look at it as a nail and just try to say, I'm going to use quotient rule, right? I'm going to rewrite this as, x represents 1 to the 3 halves, and I'm going to do it that way. It's very ugly, and you're going to lose track, or you're going to be wasting so much of your paper doing it. Whereas if you just utilize this in terms of logs, and take the natural log of both sides, you get something that's very, very easy to work with. And so you'll get a practice problem like that tomorrow. Just in case, and I'm going to get into it at the start of my next lecture. Most of our next lecture is going to be L'Hopital. I'm not going to fully get into, and I do want to at least show you a proof of it. But just so that maybe if there is time tomorrow in the workshop, you can maybe practice a little L'Hopital ahead of the times of the problems. I just want to note, and we're going to talk about, and I'll redo this tomorrow, in our next lecture, the indeterminate forms and L'Hopital's rule. It's kind of like the beginning of our next lecture. And all I'm going to leave it at is the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of f of x over the limit as x approaches a of g of x. That if this would give me f of a. So if the top limit, gives me 0 and the bottom limit gives me 0, so this gives me f of a over g of a. If this gives me 0 over 0, okay, basically saying that these two limits go, then we can apply L'Hopital rule that says if the limit as x approaches a of f of x over g of x is equal to 0 over 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. And I will show you why in our next lecture. All right? I'm not going to go through it. You probably have seen at least the most this version of L'Hopital's rule in its most simplistic state. We will evolve and go into much more depth in our next lecture, but of course you don't have a workshop in our next lecture, so I'm not going to go into too deep. I will prove why. There's always this thing, and if you take an AP exam, why do I have to show it like this? I'm going to show you why, because that's where the proof comes. It is 11:50. Have a good day. I wanted to Calc 2, Lecture 2. It's always getting used to the visual. And it looks like that's a pretty high quality projector. I think that's very clear, and everybody from the left side can see, or your right, I guess you can see, and of course you're good, right? You're very happy over there. So I'm going to start off with some stuff that you covered in workshop, in that you're going to have a formula sheet. So when I give you the quiz next week, and when you have your midterm and your finals, there will be a provided formula sheet, and I will keep updating that formula sheet as we go through the course of what's going to be on there. And so on the formula sheet, I'm going to give you a few formulas for trig and for trig. So you sine of A plus or minus B, all right, the sum and difference formula, which also, by the way, works with the same as the double angle. So if we have 2A, and we want to know what is a sine of 2A, it's the same thing as A and as B is equaling A. And it should be definitely something that you know, 2 sine A cosine B, or it's 2 sine A cosine A. That formula could help you with some future derivatives, because if you're trying to differentiate and you have to do as our integrals, and we're trying to do some complicated problems where the 2x might be a problem, you could of course utilize that formula to make the derivative a lot easier. Sounds like, well, what? That doesn't sound like, why would I, or the opposite. If you have like 2 sine x, you have sine x cosine x, and then you have some other piece, and you're like, oh, that's ugly. Well, why don't you just merge that into 1/2 sine of 2x? That can be something that can be very helpful. So we have sine of A cosine B plus or minus sine B cosine A. And what the plus minus piece means is that if it's plus, we use plus. If it's minus, we use minus, which is different than cosine of A plus or minus B, which would give us cosine A cosine B minus plus. So if we have a plus, it turns into a minus with the cosine. And if we start with minus, then it becomes a plus. This is also why we have cosine squared, or we have cosine squared A minus sine squared A in the when the double angle version. So sine A, sine B. All right. So again, these two formulas will be given. Hopefully, you touched on them during your workshop. It's in terms of it's not the first time you see it, because we're about to use these formulas. We also covered a couple formulas on the basic trig limits. You saw why they are true during your workshop. And of course, that is that the limit as theta approaches 0 of sine theta over theta is equal to 1. Similarly, the limit as theta approaches 0 of theta over sine theta is going to be 1 from the squeeze theorem. And the limit as theta approaches 0 of cosine theta minus 1 over theta equals 0. And of course, that second formula comes from utilizing your trigonometric identities, multiplying by the conjugate, getting cosine squared minus 1, And then, of course, that's sine squared, and then utilizing the basic trig limit, of course, to get there. So again, these formulas will also be provided for you on that formula sheet, and I will update them. Okay. So where does that take us? Well, that takes us to trig derivatives. So similarly to how I did how last lecture occurred, I love understanding why these derivatives work. So why is it not just, because I had it when I was in high school and I took calculus the first time, it was just a trust fall for a lot of the derivatives. This is the derivative because it is, and you look at different things and you can see how the property matches. But I always wanted to know and make sure that we know why we're able to do what we're able to do. So the derivative with respect to x of sine x using the definition is equal to the limit as h approaches 0 of sine of x plus h minus sine of x all over h. Okay, so it looks very similar to what we were doing in our first lecture, a lot of definition of derivatives. But what we see here is that we have this sine of x plus h, which is the formulas from right here in terms of x is a and h is b. All right, so we can utilize that for our next piece. So limit as h approaches 0. And I always know, yes, the question that's to answer you before you ask, these are fair game for assessments. These are fair games for your quizzes, fair games for your midterm, fair game for your final, of me asking you to using a definition to find a derivative of sine or cosine or any of those trig derivatives. So we would get sine of x cosine h plus sine h cosine x minus sine of x all over h. And so what we're seeing here, just to make sure we're seeing and we're following what my work looks like, that's where I use the trig formula right there. Really am a fan of that quality projector. Just mention having that in your living room, right? We can see here as well that two of these terms have sine of x, okay? So what I'm going to do, and I'm just so that I'm not doing every single little individual step, I'm going to combine the sine of x terms and factor out that sine of x. So this first term and that second term, which gives me the limit as h approaches 0 of sine of x times cosine h minus 1 all over h. Okay, so that what I did here is I combined this term with this term right here, and of course making it over h, plus the limit as h approaches 0 of cosine x sine h over h. All right. Now, given that, remember, h is our variable. We're taking the limit as h approaches 0. So anything that's not dealing with an h is, in a sense, treated as a constant for that limit. So we would have sine of x times the limit as h approaches 0 of cosine h minus 1 over h plus cosine x, times the limit as h approaches 0 of sine of h over h. And from what we just learned and had some pieces, this limit goes to 0, and this limit goes to 1, giving me, voila, all that's left over is cosine of x. So we just confirmed that the derivative of sine of x is always cosine of x. Okay. Questions on anything of following, along with that algebra, along with that trig? Okay. In workshop tomorrow, I'm not going to do it here because I always feel it's a good practice for you. So I'm not going to do it, but to the RFAs as well. I always like in tomorrow's workshop doing the derivative and proving it that of cosine of x and proving that that is equal to sine of x. So just giving yourself a little bit extra practice. I don't want to redo the exact same. There is a lot of similarities into it. I could prove it. It goes the same way again, but we have this other derivative right here. The derivative equals negative sine of x. Thank you for those facial expressions I see out there sometimes, and it's always a good cue. But I do want to show some of the other ones. So knowing these two derivatives. So now we know two derivatives. Technically, we've done them through definition of derivative. I'm not going to visually show you, but let's assume that we have the proof of this one as well, given the definition of the derivative, given that you're going to do it tomorrow, just so that you can see practice. We can use these two pieces of knowledge to give us our next one, and that's the derivative of tangent of x. And we know that the derivative of tangent of x would be the same thing as the derivative of sine x over cosine x. And this is one that you might have seen very similarly. Again, I could ask you to utilize the definition of the derivative for this. All right? So I'm not going to do that right now in the proof because I can prove it a different way. I can prove this using what? What's the other way I can use the proof? I can now. Quotient rule, yeah. Okay, so I can use the quotient rule, which means that this derivative is equal to the derivative of sine of x, cosine x, minus the derivative of cosine x, sine x, all over cosine of x squared. Of course, and I'm going to use the notation of cosine squared x. I just want to make sure that you all understand how that notation looks. There's other ways of using this notation. Maybe some of your instructors use these. Utilize the prime symbols right there for the derivative. They're both the same. You can also, of course, just say what the derivative is, but my feeling is, especially in lecture, we want to visually see exactly those steps that we're doing. This gives me cosine x minus negative sine x over cosine squared x. That is now cosine squared x plus sine squared x over cosine squared x. And what relationship are we seeing here?
Cosine squared x plus sine squared x is 1.
That top part is just 1. Okay, usually we hear sine squared x plus cosine squared x, but it's the same thing. Cosine squared plus sine squared of the same variable is 1. This gives us 1 over cosine squared x, which is the same thing as you've already learned, secant squared x. And so the derivative of tangent of x is secant squared x. A lot to cover today. I love it. Some extra problems for workshop that you might be working on tomorrow that can give you some extra practice. Again, they're all fair game of asking me to use the definition of the derivative, but I'm just going to state them here. The derivative of secant of x is secant x times tangent of x. the derivative of cosecant x is negative cosecant x times cotangent x. The derivative of cotangent x is negative cosecant squared x. If you haven't done one of these problems, or if you haven't done them using the definition of the derivative, I would take the time to practice that. Maybe if you're unfamiliar, maybe that is one of the problems that you may personally work through during workshop. We try to give us sometimes a little variety of the different problems. I do recommend there's going to be a lot of fractions, right? And then you have to make common denominators before you can utilize those sines and cosines. The trick here, though, is, of course, turn everything into sines and cosines, okay? And then take the derivatives. I don't expect you to memorize the sum and difference formulas for, like, tangent and all those ones. It's not required. If you do know them, of course, you can go at that way, but I don't recommend it. Move it to sine, cosines, and go there. Are we all good on these? Always feel free to pause me down. I get a little excitement when it comes back to interface, and I know I can go, especially on that first lecture, I can go in the first two lectures, I can maybe go a little too fast, I might talk a little too fast. I always look forward to the summer and getting the chance to teach this type of material and at the pace. So sometimes I can go a little fast. All right, we have one type of main derivative. Well, I guess we have more. Our next one, and this proof is not on the exam. So we're going to do the proof. This proof is not on the exam, so don't worry about this one. But I do really enjoy the following proof that we're about to see. This is what is referred to as a weak proof. Okay? And the idea with a weak proof is we know what the final answer already is. And we're going to use our answer and kind of reverse engineer with that part and say, well, if we know what it is, then we just have to make a truth statement that the left side is equal to the right side. And that's what we're going to do right now. So, and that is with the derivative of e to the x, which we know is e to the x. So if this is what it is, how is that true? And that's our goal right now, is to show that the left-hand side is equal to that right-hand side. To do that, we're going to use definition of the derivative. It says the derivative of e to the x is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h, which is equal to the limit as h approaches 0 of e to the x times e to the h minus e to the x all over h, which gives us e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. And what we're saying here is that this is equal to the derivative of e to the x, right? Which we know should be equal to e to the x. All right. So for this proof now to now finish this proof, we must prove what?
Limit h approaching 0.
There we go. That this limit in here, the limit as h approaches 0 of e to the h minus 1 is equal to 1. Because e to the x times 1 is e to the x. So our goal here, we must now prove that the limit as h approaches 0 of e to the h minus 1 all over h is equal to 1. Okay. If we can do that, we've now proven that the derivative of dx is equal to dx. So now it becomes a little different piece. You know, can hear that good typing. From pre-calc and from finance. I teach financial literacy. I actually got a finance degree from here. Never actually did end up getting my math degree from MIT. After a bit, it becomes so abstract that I didn't find. I was double majoring. And so I ended up finishing my degree in finance and in business. And, you know, I teach right now. One of my main courses I teach is financial literacy, credit, taxes, investments, retirement stuff. Find it very important. Should be very, very important for you as well if you have that. If you haven't opened up your Roth IRA yet, do so. And that gives us this formula to limit our high yield savings account too. Every single one of you should have one of those as well. The limit and I'm going to use big H, approaches infinity of 1 plus 1 over H. And this is the compounding interest formula. That's why I'm bringing this up. To the H is equal to E. All right. So that's where the compounding, exponential compounding, every single millisecond, your money is being compounded. Of course, in the real world, your money is compounded usually in terms of interest being added, once a day. You can have it every year. You get your interest every month. You get your interest every day, every minute, every second, every millisecond, and ends up getting this formula E. And that's where we also get that kind of when we turn the formula to like e to the RT. That's where this comes from as well. Comes from this understanding of this formula. All right. So this is something that we already know that's true. And what we're going to do is we're going to define, and the hardest part that what I'm about to show you is that we're going to do a lot of changing of variables. All right. And it can get a little tricky in terms, but it's like, well, why did you choose that? We want to kind of make it, remember, our goal is to kind of make it like this. That's our goal. So I'm going to define B, just this other variable, as e to the H minus 1 over H. Basically, I'm going to define this piece in here as just a terminology, a term B, okay? So I want to find that this B, and since there's all these different terms, I want to turn it into one single term, okay? If I do that, therefore, e to the H is going to equal 1 plus B times H, which means that B times H is equal to e to the H minus 1, okay? And then we're going to define big H as 1 over B times H, which therefore means that 1 over H is equal, big H, capital big H, sorry. Big H equals 1 over B times H. So 1 over big H is equal to B times H. And as H approaches 0, big H approaches infinity. All right, now that we have all that, we can now substitute our information that we have in there. So from our pre-calculus information, we know this is from pre-calc again, our finance. E is equal to the limit as big H approaches infinity of 1 plus 1 over H to the H, to the big H, which therefore will equal the limit as big H approaches infinity of 1 plus B times H, okay? And actually, let me change the color on that because I'm just so you can see the substitution happening. B times H raised to the B times H. This now, so now we have E, so therefore E is equal to the limit as big H approaches infinity of that whole part on the inside, 1 plus b to the h, right, is e to the h. We got it right here. So e to the h raised. Oh, sorry. B. Where's the what? Oh, it should be over here. Sorry, yeah, that should be 1 over. That's where you're catching, right? Yes, I always miss that little tiny thing right there. 1 over b to the h right there. Sorry about that. That's the big key. I was like, wait, where is it missing? Perfect catch. So e to the h to the 1 over b times h. Okay. Now I'm going to flip the limit, all right, from h to little h. So this now becomes the limit as little h approaches 0, because that's big H, little h approaches 0. And I'm going to just do some algebra here. This just becomes e to the 1 over b. Okay? All right. So now the e is the same thing as e to the 1. So now I have e to the 1 is equal to the limit as h approaches 0 of e. Oh, I'm sorry. I meant to do that. Sorry. So this function here, this is a continuous function. Does everybody understand that? E is a continuous function. All right, that's very important. And one of the things we talk about in limits is that if we have a compositional function, if we have a continuous function, and actually I'm going to write that inside my little side notes here. So it's a little side note. If f of x is continuous, at x equals a, then the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. You should have probably seen that in your first part of limits. You can actually bring the limit through, but it's only something that's true if the function is continuous at that point. Okay? Why is that important? Because this is a compositional function, e to the 1 over b, right? E to the x, your g of x in this case is 1 over b. So I can say that this is equal to e to the limit as h approaches 0 of 1 over b. Okay. So now we have a new proof that we have to prove to make this true. All right, we have one more part. I know, right? That's why I love this one. Well, first off, this is a true statement. This is not part of the proof. Sorry, this is a true statement. This is a true statement from what we've manipulated. And the reason why that's helpful is because now we have, in a little semi-proof, we have proved something along the way, is that the limit as h approaches 0 of b must be what? It must be 1, right? Because 1 over 1 is 1. The numerators have to equal each other. So this, basically must equal this, which the limit can go on the bottom of the fraction as well. Okay. Woo! Not done yet, the proof yet. Because remember, we did a lot of substituting, and we have to go back to that e to the h minus 1. So we now know that this is true. But remember, I said that basically this whole thing inside of here is b. So remember our goal, the goal that we set was to show that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1, which is equal to the limit as h approaches 0 of b. Put the two together, and we've now shown that this is in fact a true statement. All of that was just b. And the goal was to show that that limit of b was 1. And we did it. Now we have proven. So the derivative of e to the x is e to the x.